Hello and welcome back. Mrs. Saunders here. Today we are looking into the so exciting world of absolute and conditional convergence. I'll explain what that means as we go. So far, we've been asking whether or not a series converges or diverges. But there is another layer that we can add to this question. If the series converges, does it converge absolutely or conditionally? Now, alternating series are more likely to converge than non-alternating series. That's important. When we take the absolute value of a series, we remove any alternating signs. So we're just looking at the size of the terms. All of what we've learned so far about convergence is now in play. Absolute convergence. It means that the series made of absolute values converges. If this happens, the original series must also converge. Conditional convergence. This is trickier. The original series does converge, but its series of absolute values does not. This means that the convergence depends on the alternating signs. In short, we're asking, does the series only converge on the condition that it's alternating? Let's look at an example to clear that up a bit. On the top left of your screen, you'll see the harmonic series. The harmonic series is a p-series with a p-value of 1, which diverges. Next to it is the alternating harmonic series. And we've seen in a previous lesson that this is a series that converges. So this would be considered conditional convergence because the series only converges on the condition that it's alternating. Now, on the bottom, we have the series 1 over n to the 4th. This is a p-series that converges because p equals 4, which is greater than 1. And if we make this an alternating series, it still converges. The condition of alternation doesn't change anything, so this is absolute convergence. Example 1, determine if the following series converges absolutely, converges conditionally, or just diverges. So we have this series, -3 to the n over n factorial, and it's that -3 to the n. That means it's an alternating series. So first thing we need to do is to take the absolute value of it to remove its alternatingness. So now we just have the series 3 to the n over n factorial. Does this series converge? Again, all we've learned so far is now in play. So I'm going to bring up this menu of convergence tests, and which one shall we use? It's a bit of a complicated series, so I'm thinking the ratio test, and I'll go through this part kind of quickly. So we'll take the limit as n approaches infinity of the n plus 1 term divided by the n term. And we're going to cancel out some stuff. And as n goes to infinity, we get 0, which is less than 1. So the series converges without alternating, which means it's for sure going to converge if we add back in the alternatingness of it. Therefore, we'd say that this series converges absolutely. Let's try this series, -1 to the n plus 1 over the cube root of n. Okay, so it is alternating, and we're going to take the absolute value of it to get just 1 over n to the 1/3. That is a p-series with p less than 1. Okay, so that diverges, which means we're going to need to look further and reconsider this back as an alternating series again. So we're going to use the alternating series test. So now we're going to check. The limit as n approaches infinity of a sub n, does that go to 0? Yes, it does. If we check out the terms, they are decreasing. Yep, they are decreasing for all n. So as an alternating series, this converges. Therefore, this series converges conditionally. It has to be alternating in order for it to converge. Pause the video and try this one on your own. We have an alternating series, so the first step would be to take the absolute value, and then we get n over n plus 2. Which test would you test that one on? Now, don't forget about the nth term test. That's one of the first ones we learned, and it's really important because, watch this, the limit as n approaches infinity of n over n plus 2 is 1. It's not 0. So right off the bat, this diverges. So we need to look further and reconsider this as an alternating series. Now again, because of the nth term test, this one diverges. The alternating nature of it doesn't help. Now, why are we doing all this? Just a reminder that our end goal is to figure out how long a power series works. A few lessons ago, we learned the ratio test to help us find the radius of convergence. Do you remember this problem? We found the radius of convergence is 2, but what we didn't know at the time was what happened at the endpoints of the interval. We now have all the tools we need to complete the picture, and the whole answer, including the endpoints, is called the interval of convergence. To review, we have 3 possibilities for when a power series may work. If the ratio test gives us a result less than 1, then the series converges to an interval. If the ratio test gives us a result that equals 0, then the series converges for all values of x. If the ratio test gives us a result of infinity, then the series converges only to the center, x equals c. So let's finish this up with a few examples. Example 4, find the radius of convergence and the interval of convergence. The first part of this process should look familiar, so I'm actually going to go through the first part kind of quick. If you feel like it's too quick for you, go back and watch the 10.6 lesson just to review how this first part works. First, we are going to employ the ratio test. We'll take the absolute value of the n plus 1 term divided by the n term, and we'll clean it up a bit and cancel some stuff out, and then take the limit as n approaches infinity, and we end up with the absolute value of x minus 2. So our power series will converge when the absolute value of x minus 2 is less than 1. So we'll solve that inequality and get an interval of x that works between 1 and 3. Now, we need to check to see if the power series works at 1 or at 3. We need to check the endpoints. So let's plug in 1. We're going to plug in 1 to our power series. That gives us the alternating harmonic series, which we know converges. All right, so let's see. If we plug in 3, oh, that's just the regular harmonic series, which diverges. Our power series here is centered at 2, so we have a radius of convergence of 1. Therefore, our final answer is this interval of convergence. Any x between 1 and 3, including 1, but not including 3. That's a lot, isn't it? Go ahead and go back and watch that one again if you need to. Y'all, these take a lot of practice, so we're going to run through a couple of examples still. This one, we've got negative 3 to the n, x to the n over the square root of n plus 1. So again, we'll run the ratio test on that, taking the n plus 1 term, dividing it by the n term, and then we're going to let n head to infinity. Those n's have matching powers and matching coefficients, so those go to 1, and this whole thing simplifies to the absolute value of negative 3x. Now we know that our power series converges when the absolute value of negative 3x is less than 1. So solving that, we have an x between negative 1/3 and 1/3. Okie dokie. Now, again, we have to check the endpoints. So we'll plug in negative 1/3, and let's simplify that. Okay, now we have to see if this series 1 over the square root of n plus 1 converges or diverges. For the sake of time, since I know you're a whiz at convergence and divergence tests, I will tell you that this one diverges by the limit comparison test. Next, we have to plug in positive root 3, and we'll simplify that. And this one converges by the alternating series test. This power series is centered at 0. We have a radius of convergence of 1/3 and an interval of convergence of negative 1/3 to positive 1/3, but including positive 1/3. Just a few more. Once again, let's employ the ratio test, and I'm going to simplify it for you just so that you can see what happens here. Do you see how all the n's are on the bottom when we clean that up? So this one, as n goes to infinity, goes to 0, meaning there are 0 places where this power series doesn't work. So our radius of convergence is infinity, and our interval of convergence is all reals. This one turns out kind of opposite. When we employ the ratio test and clean it up, we only have n's on top. So this sucker just keeps growing to infinity, unless, of course, x equals 0. Therefore, we have a radius of convergence of 0 and an interval of convergence of just when x equals 0. And this is a good time to remind you that a power series will always converge at its center, but that might be the only place. Last one. Here we have a power series, a sub n times x plus 5, that converges conditionally at x equals 2. So which of the following must be true? The key to this problem is which of the following must be true. Let's start by drawing out a diagram of what's going on. We have a power series centered at negative 5. We know that it converges conditionally at 2. That's 7 to the right of negative 5. So if our center is negative 5, that means we can go 7 to the left of negative 5 to complete the radius at negative 12. Now let's check out our options here. A says the series converges conditionally at x equals negative 12. Does it? Well, maybe. It's an endpoint. We don't know for sure. And again, we want to know which of the following must be true. So not that one. B, the series diverges at x equals negative 12. Again, this is an endpoint. We don't know. We'd have to test it. Maybe that's true, maybe not. C, The series converges absolutely at x equals -7. Let's put -7 in there. Well, that is well within the radius of convergence, so we do know that. And let's just look at D real quick. The series diverges at x equals -7. Well, no, we know that it converges there. So there we are, the end of this lesson. Thanks for being here. We've got one more lesson, and then we'll be done with Unit 10. I'll see you next time.